All right, the next chapter is a nice chapter. It's a very meaty chapter. It's one that I think a lot of people have been waiting for. It's all about some real pumps and turbines and piping systems, okay? Very applicable. So it's entitled Turbomachinery, but it's really dealing with pumps and turbines. It also deals with compressors. It deals with fans. It deals with air turbines, hydraulic turbines, steam turbines, just a whole smear of things. But let's just start simply by thinking of water pumps. And then we'll connect the water pump to a piping system. And then see how they operate together, the pump in that system. Here's a pump. It's a dynamic pump, meaning that you bring in fluid into this pipe into the middle of this pump section. That pump section is driven by a shaft that's aligned with the inlet pipe. And if I turn it sideways, it has a rotating section that cuts into the fluid and throws it out. Collects in a region and sends it in a discharge pipe. That's a pump. Okay, that's what a pump does. It's driven by this, which is an electric motor. It's just a shaft running over, and this is a shroud to protect some worker or anybody else from getting hurt by a rotating shaft. Very dangerous rotating shafts, right? Be very careful. Loose clothes, hair. So that's a picture of a pump. It's radial flow, meaning it brings it in the middle and throws it out radially. Collects it up and discharges it. It really is the diameter of this inlet pipe and the diameter of that outlet pipe. They're typically, the suction is a little larger than the discharge. But for first introduction, just say they're the same diameter, okay? If they're the same diameter, even though the fluid may be very fast coming right off the tips of this rotating part here, they slow down and build up pressure, and this pressure coming out is a lot higher than the pressure going in. That's what a pump does. It really isn't. Inside the pump, it imparts a lot of kinetic energy or a lot of momentum to the fluid, but that fluid then is converted in another part of the pump into a higher pressure. And the goal of the pump is to boost the pressure across the pump. You can see that this one looks like a larger suction line than the discharge, doesn't it? So a lot of times in practice they are large on the suction and small on the discharge. Okay. So what are the parts? You can take a look at a good graphic, but I thought I would just build it. So what you have is an eye region. The fluid comes into it and turns 90 degrees and goes into an impeller region. And that impeller region is rotating, and I'm just going to show a couple impellers on it like this. And the fluid then, after it turns a 90, flows through that between the impellers. And the impellers cut into the eye region, and they sling it off the tips. So if you look at a velocity diagram of the tip, its tangential speed is high. The fluid is coming off, sliding along the vein, right? Coming off like this. So that's two vectors. You put them together to get the actual fluid velocity by a velocity diagram. So it's coming off really fast. Alpha those impellers, okay? And then they're caught up, get rid of that velocity diagram, in a casing. Here we'll put the casing, maybe we'll start it here. It'll be very small, and then it'll get larger, 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 until you discharge. And there's a cut right here, okay? Because it's like accumulating, 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 getting more and more. That's why it has to increase in size. Flow added to it until it's finally 100% leaving. So the flow comes in the eye region, goes through this impeller region that's rotating, and in the casing it's collected up and then converts a lot of that high kinetic energy into a different form of energy, the higher pressure. From Bernoulli's equation, you can see that. And discharge. Okay.
The eye is like is the water coming out of the screen?
Yeah. And so if I turn this sideways, and I'm going to try and put it here, over to here, and here, over to here, and then here, over to here, and here, over to here. What happens is you're coming in this way. I've turned it now, a different view, and the fluid's going to come in, and it's going to turn 90 degrees, all right? I'm going to try and draw it like this. All right? It's some of it, you know, go into different sections, like it'll go into this section, this section, this section, that section, that section. You just have a top and a bottom, looks like two sections, but it's more. And so this would be the beginning right here, and then discharge. And so it's actually turning it. A lot of them, they have a nice blend to it where they turn it, now it's coming out radially. So it's a 90 degrees turn. Some of them, it's a hard 90. Some pumps are really cheaply made. Some of them, they spend a lot of machining time and engineering analysis time on, such that they're efficient. The mechanical efficiency is higher. And then this, yeah, it's going to be helpful. This is all connected up with a shaft, and this all shaft is rotating like that. And so this is showing you the fluid passageway, and the fluid comes in, goes out off of those impellers. It's collected up in a region here, and then maybe up here it's even larger region because it needs to discharge into the pipe. Larger region. Okay. Well, where is the pressure the lowest in the whole system? Lowest pressure. It's right in the eye. It's being, in order for the water to go from here to here, it has to be lower pressure. So the lowest pressure, right as it's starting to get cut into the veins. Where's the highest pressure? Well, in the veins, there's some low pressure regions as well. Okay. In the veins, this side right here, it's catching the water and it's high pressure. On the back side of the vein is really the region of lowest pressure. All right. But we'll get into cavitation in a minute. Okay. But inside where those impellers are, some regions are very high pressure, some are low pressure. Okay. And then the discharge is your high pressure. That's where your highest pressures are. All right. So the pressure on the out is greater than the pressure on the in. There's a lot to understand about pumps. Let's go through it slowly by maybe setting up a test system for a centrifugal pump. So we'll have a supply tank that's plenty of water in it. Not going to run low on water. And it'll come into a pipe, and one of the things we need to know is we have to measure our flow rate. So we have a flow meter. What does it tell us? It tells us the volumetric flow rate. Okay. Then it's good to have valves so that we can control things. This valve, if I need to work on a system, I can shut it all the way off, right? Then disconnect everything to the right of it. Or it could be a throttling valve where I close it a little bit and give some resistance to the flow across the valve, right? Or maybe I open it all the way up and let the flow go through with minimal resistance across the valve. That's the type of valve I'm talking about. Think of it being fully open, fully closed, or even partially closed. Now we come in to a gauge. I want to measure the pressure. So this is a pressure gauge right before it goes into the pump. And I'm just going to put the pump here. A lot of times they put round looking objects for pumps, right? But I put a box for the flow meter. I put a box for the pump. Doesn't mean I have a square pump. It's just I'm lazy. I don't want to draw a round pump. And then it comes out, and we have right away another pressure gauge. So the pressure gauge right there. Then it's going to go through a valve that I can control. Maybe I want to turn it down, open it up, and then let's just discharge it. And when it discharges, we'll have to collect it. So we'll put a tank right here to collect it up. But that tank's big enough to collect up a lot of water. So there's our test system. Now, if you measure the flow rate or the capacity, AV, right here, and it's liquid water, is it the same as the flow rate coming out at the end of the pipe? It's the same flow rate, right? The volumetric flow rate's the same. It's incompressible, it's liquid water, mass density is constant, volumetric flow rate is also constant. We talk about the head, or we also talk about the head is lowercase h in units of meters. We could talk about cap H in kilojoules per kilogram, or we could talk about the pressure head in kilopascals. All three units are good measures, right? So I may have a pressure gauge right here, but you know that pressure gauge may tell me meters of water column. Maybe somebody says, I want a really long manometer there. Great, put a long manometer there, and that'll actually show you the meters. But you may need something that goes over 100 meters, so that's ridiculous, right, of a manometer. But all of these are measuring your head. Head in meters, or energy per unit mass, kilojoules per kilogram, or pressure in kilopascal. I could jump back and forth between these units. Divide by rho g, multiply by rho g, right? Divide by g, divide by rho. All right. We're going to talk about the water power. What is the power that gets into the fluid, the flowing fluid? It has a higher mechanical energy flow rate coming out of the device than coming into the device, the pump. What is that, W dot F? Is it maybe this head times rho g times AV? Does that equation make sense to you? Does it? Yeah, it's the head gain. I should put a gain right here. The head gain across the pump, or it's equal to the pressure gain across the pump times the volumetric flow rate. All those units and equations hopefully make sense to you. It's the mechanical power put into the flowing fluid. That's what we want the pump to do. You can see it most clearly by the pressure gain times the volumetric flow rate. That product is the fluid power that we wanted to get into the fluid, right? All right. What about the pump is driven by a shaft? I'll just draw it over to the side. And the shaft is rotating with the rotational velocity omega, and it has a torque in that shaft. Can you calculate, as good mechanical engineers, what's the power being transmitted into the pump by the shaft? What is that flow of mechanical energy coming into the pump, the shaft power? Isn't that the W dot shaft? Isn't that the product of omega and tau? Thumbs up if you like that. Good, right? Isn't it? So this is what they call the shaft power or the brake horsepower, meaning it's mechanical coming in to the pump. Guess what the efficiency is? The efficiency of the pump is I wanted to get into the fluid. I wanted that power to go into the fluid, but not all of it does. Whoops. Only so much goes into it of what come into the shaft. So the ratio of the fluid power to the shaft power is my efficiency. It's converting from shaft energy or shaft work into the fluid work, fluid power. That makes sense for mechanical efficiency of the pump? Good. Now, this is a free capacity. So what we do is we let the pump be fed with a lot of water. No restrictions on feeding the pump. It's not starved at all. And we put no restriction on the outlet. It just is blowing out, right? You ever seen a pipe where they just let it go? There's maybe a fire hydrant when you're a kid or something. They just open it up and let it rip. Okay, well, think about that. The pump is throwing as much fluid out as possible. If it does that, the pressure difference or the pressure gain across a pump is minimal. It's minimal. It's just sort of like catching it and slinging it without adding any pressure to it. That's the highest flow rate through the pump possible. Other than that, you're going to be like, forcing it through with a pressure that's going to be higher on the inlet than the outlet, right? Don't do that, right? This is a free capacity. So at the free capacity, your delta P gain is 0. Okay. Now you take it, say, shut-off head. What's that? Take this valve on the outlet, start closing it. Close it and close it and close it until it's closed all the way, right? And I have a big sturdy pipe and I have a big valve. It's not going to break. And I shut it off. And you know what? The motor's still driving that pump. The pump's still running at 1800 RPM or 3600 RPM, right? Okay. So what happens is, what do you think the pressure in this outlet gauge does? It goes way up. And it goes to the maximum that it's going to go. And the suction pressure is still low. And now I have the maximum delta P across that pump. All right? So what we do as engineers is, let me erase right here. I'm going to stick a plot up here. On the x-axis, we'll plot the volumetric flow rate that goes through the pump. We measured it with the flow meter. It's sometimes just given a symbol Q. I don't like to give it the symbol Q because it's so confusing with other Qs out there. But its units are meters cubed per second, or liters per minute, or gallons per minute. It's some volumetric flow rate. We're talking water pumps. On the y-axis, we'll talk about the head gain across the pump. It could be meters. Fine, just do it. If somebody wanted to convert that to pressure, no problem. And so we can plot 2 points on here. One is the point where you had the free capacity. You had the highest volumetric flow rate, but no head gain across the pump. And then you started to close the valve. And as you closed the valve, you got another measurement. And then another measurement, then another measurement, then another measurement, another measurement, another measurement, another measurement. And you know what? These are kind of boring plots, but that's what they look like. They just kind of go here, flat, kneel off, and kick down. That's your pump characteristic curve. So it's a for that pump running with the motor driving it at a constant RPM, that's how it would behave. From the shut off, this is the shut off, sorry, right up here, the shut off head, to the free flow, free head, free flow capacity. Okay. Can you get a flow beyond that? No. Can you get the head above that? No. You can't get a head above that. We start with the axis 0, 0. 0, 0. Okay. Let's do this. Let's take a look at our equation for the efficiency again. Our equation for the efficiency was what went into the fluid divided by the shaft. Okay. The shaft is our torque times omega. What went into the fluid is our head gain times rho g times AV, the volumetric flow rate, right? See how, did I do that right? Can you tell me what is the mechanical efficiency where you had free flow through it? The highest volumetric flow rate but no pressure gain added by the pump. What's the efficiency right here? What is it? 0. I heard somebody say 0. Why is it 0? Because no pressure gain right there. It has no efficiency. All right? It's 0 efficiency. There's power being supplied to it, but it's not really boosting, putting energy into the flow work. Okay, let's take a look at this point right here. It's 0. Why? The flow rate's now 0. The head gain's high, but the flow rate's 0. And if you move out somewhere in here, maybe it's 25% mechanical efficiency. Maybe it's 25% mechanical efficiency. Maybe if you move out here, it's 40% mechanical efficiency, maybe 40% mechanical efficiency. Maybe right in here you get the maximum at 70% mechanical efficiency. Does that make sense? And you know what? That's called, and for this curve, the pump performance curve, there's one point that has the best efficiency point. It's called the BEP, best efficiency point, right there, 70%. It'll not always be the same. Some pumps will have a higher value, some a lower value. I just made up these numbers. All right. Now, as a manufacturer, we were introduced to this idea of impeller and a casing. They like to make a casing and then put the maximum impeller in it and then a few sizes smaller so that they can sell one casing with different impellers, so it's different models of the pump, but they can have control of logistics, right? Manufacturing makes sense. You have to have all the warehouse, all these pumps and everything else, right? So what they'll do is they'll change the impeller diameter. They'll have a big one, the maximum that'll fit in that casing. They'll drop it a little bit, and they'll get another curve. And then they'll drop it, and they'll get another curve. And usually they get about 4 curves, and that's enough. I mean, you're getting too small. Well, you don't want to go below that in that casing. Go get another casing, another pump, all right? And so each one of these will have a best efficiency point, and a best efficiency point, and a best efficiency point. And they'll have a recommended range of operation. The way they do that is they look at the flow rate at the best efficiency point. They multiply by 1.1, they go about 10% higher, and then they go about 0.8, so 80% lower, and they say, if you want to run with that impeller and that casing, try to stay as a design engineer in that vicinity. Don't go to the other parts of the curve. It's not worth it, okay? Operate close to the best efficiency point around that curve. So they'll say also for this one, they'll come down to the flow rate, 1.1, 0.8. They'll get a region like that. And this one, and then this one. And so they'll get a region that's a map like this. And they'll say, for that casing, with all of our impeller designs, that's where this pump you should run. Okay? That's where you should run with this pump. Here's a centrifugal pump curve from a manufacturer, okay? They make a lot for the air conditioning and hydronic systems, water systems associated with chilling, chillers and heat and boilers and stuff in buildings. What do they have on the x-axis? Flow in gallons per minute, GPM. Goes from 0 up to 1,000 for this pump. Okay, for this is model, I just picked a random one. You can get these off the internet. Model 1229. Okay, it's to be driven with an electric motor at the speed of around 1,200 RPM. Just a little bit below 1,200. That's the way electric motors run. You would say it's a 1,200 RPM motor, but it's really going to run full load around, rotated around 1160 RPM. All right. Now, they have a maximum impeller of about 11.3 inches. Then they have 11-inch impeller, then 10, then 9, then don't go below 8.3. They won't sell it. Doesn't make sense to sell it below. Get a different pump. Go to a different model. Okay. Notice feet and head. Did I say feet and head or head and feet? Head and feet, right? Head and feet. Now, somebody says, I just learned all these liters per second. No problem. The other x-axis. And I learned all these meters, head and meters, the other y-axis. We're bilingual. How do you like that? Right? So we have the meters over here and the liters over here. And you can see that they have a curve of 83%. It goes like this. What is that 83% curve of? The mechanical efficiency. And this curve right in here is 84%, right? And then this curve is 2%, right? so you could see the efficiency curves. Now they put them even outside the region that you would want to operate this pump. Down here, you don't really want to be operating down there, nor in here. But they don't even extend these all the way down, do they? You don't want to be operating way down there. This is where you want to operate, okay? Even a subset of this shown on this plot. So they put a lot of information on these plots. Let's do this. If I was to say the best efficiency point on that one looks right there, looks right there, looks right there, looks right there, looks right there. Read down, maybe this is 540 GPM. Multiply that by 1.1, it would come over here somewhere. Multiply that 540 by 0.8, it would come over here somewhere. This is the region that I really want to run that pump. I really don't want to run it otherwhere. You just start falling off on efficiency. And then you would get a whole suite like that. That's where you would want to run that pump. Don't be trying to go down in this region or any other region. Just try to run it in this shaded region. Okay? You would be changing impellers to change some of it. Now, what do they show you right here? 7.5, 3. What is this? Can you read that? This is 10 bhp. bhp. bhp for brake horsepower. What motor size do I need to put on there? So if I'm going to be running that somewhere, anywhere to the smaller than that, it'll all run with a 10 horsepower motor, no problem. Anywhere, this curve is a 7.5. Anywhere over here, 7.5 will run no problem. But if I want to run this guy at this region right here, and I strap on a 7.5 horsepower motor, it's going to strain. It's going to be overloaded. Or let's say I put a 5 horsepower motor on, and it's out here, and I picked this 11-inch impeller, and I'm trying to run right there. I've got problems. I don't have a big enough motor, right? So often what they do is they pick a big motor, and a little bit of over-speccing on motors is okay. It's not going to kill you. It's just going to cost more to buy a 10 horsepower motor than a 5. If a 5 would have been okay, right? But if you really only need a 10 and you buy a 50, come on, be a better engineer than that, right? You can do better than that. So that's what they're showing you here on this brake horsepower. You can get down to a 3 horsepower motor, but look, you don't want to be. This whole pump there should never be a 3 horsepower hooked up to it. It just doesn't cover enough of the range that you want to be operating in. Okay, all of this curve is typically based on water. Nice clean water with a specific gravity, blah, 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 1.0. You start changing the fluid, we'll talk about the affinity curves, how the density of the fluid affects these curves and shifts them around.
The flow rate, you control it with the valve, but the head, how do you control that?
Okay, when you put it to a system, it goes to its operating point. We'll get there. Let me do this though. Let me ask you some questions. Would you put this pump to be a good match on a 500 GPM when I needed to deliver 500 GPM to a system and I knew that that system would consume 40 or needed to be fed with 40 feet of head? Would this be a good pump for me? Come out 500, 40. I'd be running right around here. You know what? Looks good. Yes. How about 500 GPM and 65 foot of head? No. No. It's not a strong enough pump to be delivering 65 foot of head. It's too weak. Get a bigger, stronger pump. How about 200 GPM at 35 foot of head? 200 GPM, 35. It's really out of the sweet zone of operation. Oh, it'll probably do it, but better if that's where you're going to operate, go get a different pump, okay? How about the 700 GPM at 45 foot of head? 45. It can, but you might want to look at another pump. It's kind of on the edge, okay? This is maybe an okay. This is maybe a not so good okay. This is a definite no, 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 won't work, right? Okay. And this is a yes, yes. Well, there's a lot of manufacturers, and they want to be able to supply you a pump that will meet your needs. And they often put out what they call these composite maps of pumps for similar types of pumps. So they have a very large flow rate range, and they have a very large head range, right? And what they did was they put this one pump's sweet zone in here, and they have them kind of overlapping, so another pump's, let's say this one, really goes like that. It's a box, but some of it's covered up by the other pumps. And this one, you know, it's really covered up a lot, but there's a box for that pump too. But you get a sense of, oh, if I'm needing the, you know, this flow rate with this head, you know, maybe I need to look at a pump that's in this vicinity, you know. So it helps the engineer select the right pump for the problem. Okay. Notice they say they go from 80 to 110% of the best efficiency point. That's how they do the flow to determine that little rectangular shaped area on the map. Solve a problem, man. Why not? So a pump increases the head of the water from 10.2 meters to 306 meters at a flow rate of 1 meter cube per minute. The inlet and outlet pipe diameters are the same, and there's negligible change in elevation across the pump, not pipe. The pump efficiency is 77%. Determine the shaft power supplied. So find that shaft power supplied to the pump. I'm sorry, but we're about out of time, so I'm going to need to solve this problem. Is that okay? So if I need to solve the shaft power to supply the pump, what is actually getting into the fluid, and divide that by the efficiency of the pump? Okay. What's getting into the fluid power? That's going to be some head gain times rho g times AV, or head gain. You know, however you want to write it. Does that equation look good to you? Yeah. Let's take a look. The head gain is, it comes off at 306 meters, and it went in at 10.2 meters. So there's a difference in the head. That's the head gain the pump did. All right. We're doing water, so rho is 1,000 kilograms per meter cubed, and G is 9.81 meters per second squared. True? So we've got this. What's our volumetric flow rate? AV, often the book uses Q, is 1 meter cubed per 60 seconds. So the efficiency was 77%. And so you calculate the shaft power.
How did you get the volumetric?
The what?
Volumetric flow.
The volumetric flow rate was actually, everything's given. This is one of these, I just introduced the concepts, easy problem, right? Yeah, I can't find it. I think the answer comes in at 62.8 kilowatts. If you want to run the numbers for me, somebody want to run them? See if you agree. You already agreed? Yeah, so we have one agreement. Let's see, 2 agreements, good. Did you see how that's done, right? I've got a few more minutes, okay? So I'm going to try and cover just a little bit more. This is a great topic. Cavitation. It's a practical problem. Now, it was talked about way back in chapter 1 of this textbook, I believe. They talked a little bit about cavitation. So what exactly is cavitation? So you have a fluid, and if you that fluid flows into a region of low pressure. What can happen is you can get some vapor packets or vapor bubbles forming in the fluid. Then guess what the half fluid does? It then flows out of that low pressure region into a higher pressure region. Those vapor packets don't exist in equilibrium anymore, and so what do they want to do? They want to go away, and they collapse. So you have fluid flow from high to low pressure. In the low pressure region, you get some vapor packets, some vapor bubbles. Okay, all right. Then they flow right away into a high pressure region, and the bubbles want to go away, and they collapse. And when they collapse, they typically collapse right near a solid surface, and they have a pop to them in a pressure wave that goes out. And that pressure wave can ping on the surface. And anybody that's ever heard rotating machinery run and they start to run with some cavitation problems, it sounds like somebody's throwing marbles or rocks through the machinery. Okay? So loud. Sometimes you can't hear it, it's still occurring. But sometimes it gets so bad it's audible. So what exactly is it again? Gas or vapor bubbles forming in low pressure regions, flowing over, collapsing, and then impacting and sending a significant pressure pulse through, and it impacts the material, the solid material, like a boom boom, like hitting it with a little hammer, right? Or sandblasting it. Maybe that's a better analogy, because the effects of cavitation look like somebody sandblasted it after a long time in rotating machinery. So how do you prevent cavitation? Never let fluid go to very low pressure regions. Well, so what you do is you try to keep the fluid always at a high pressure throughout the system. So one of the classics is if I wanted to take fluid out of this tank and pump it up into this storage tank right here, I may have mentioned this already, and I wanted to have it routed like a piping network, go like that, right? And then just dump it into the top of that tank and it would fill it up. Where would I put the pump? Would I put the pump at location A, or would I put the pump at location B? And it makes a big difference if you're trying to avoid cavitation. Because if it's at B, you can just look at the pressure. Here it's atmospheric pressure. This is above atmospheric pressure. Oh, it's back to atmospheric pressure, neglecting any head loss. And you know you're going to have head loss, so you know at this point right here it's at below atmospheric pressure. And as you keep going up, guess what? More and more and more below atmospheric pressure. It could get so far below atmospheric pressure that it gets down in the range of the vapor pressure of the water that you're trying to pull up, and you get vapor. Right? See that? So it's easy to get fooled and think, oh, it doesn't matter. Put the pump at B or put the pump at A, it won't matter. No, it'll matter because of cavitation. Okay? So what you want to do is you want to check the pressure. You want to put the pressure, they call it the net positive suction head. The problem with the pump is on the suction side. You want the suction head at the suction line to be high enough head or high enough pressure so that you avoid the cavitation, right? So you want the pressure right there or right there, the inlet to the pump, to be high enough. You want it to be higher than required because the pump manufacturers tested their pumps against cavitation, right? All right. So how do you calculate this net positive suction head? Well, it's the head at the inlet, the static head, plus the dynamic head. A lot of times you can neglect that dynamic head, but you would include it because it does help build up pressure. That dynamic head is your V squared over 2G. Okay? Minus how far you are from just boiling the fluid at that temperature. So if I have water and it's cold, low vapor pressure. If I have water and it's hot, oh, watch out. It's going to be easier to have cavitation in 90 degrees C water than 10 degrees C water. So it's all measured relative to the vapor pressure. Okay, so this net positive suction head, I know that this vapor pressure right here is PSAT. You get that out of the table. It's a function of the temperature of the water or whatever fluid you're pumping. I like to use water. Once you have water down, you can go to other fluids. And you divide it by rho G. Isn't that then the vapor head of the water? And you need to be above that. This head inlet plus the dynamic head need to be sufficiently above that head right here. That's why there's a minus sign in there. That's the net positive suction head. Now, they have a little subscript. The pump manufacturer says the head required needs to be, 3 foot or 3 meters. Don't ever let the net positive suction head at the pump in actual operation be below 3 meters. You'll get cavitation. So the net positive suction head required is the minimum, and what's available should always be net positive suction head available. Should always be greater than the net, I can't even spell, net positive suction head required by the manufacturer. Last thing, let's go back to our pump curve that we saw. Where did they tell me as a design engineer anything about the net positive suction head required for this pump in operation? It's hard to see. You've got to look for it a lot. Net positive suction head. Oh, they didn't put the R in there. That's okay. They just said, hey, you need to have this. It's measured in feet. And they said anywhere here, see that line coming down? 16 feet. Anywhere here coming down, 10 feet. Anywhere here, oh, that's 12. This is 10. This is 8. See how they drop it? This is 4. So if you're operating kind of out in this region, watch out. You need a lot. You need more positive suction head available at the inlet to the pump. And if you wanted to, you could probably extrapolate and say, okay, if I just need 3 or 4 meters and I'm good. Or no, 3 or 4 feet of net positive suction head. Different manufacturers have different ways of displaying it, but it's always shown on their curves. Thank you for your attention.